Let's talk about gravity. It's one of those things we take for granted, right? It's what keeps our feet planted on the ground. But the real story of gravity, well, it's one of the most profound and genuinely mind-bending tales in all of science. And I promise, it's going to challenge just about everything you think you know about how the universe works.
You know, we all learn in school that gravity is some kind of force that pulls things together. An apple falls from a tree, the Earth orbits the sun, you get the idea. But I want you to hold on to this question as we go. What if that's not it at all? What if gravity isn't a pull, but a push from space-time itself? This one question is the key to a revolution that completely rewrote our map of the cosmos.
So for centuries, Sir Isaac Newton's vision of gravity was king. He imagined it as this invisible rope, right? Something like instantly yanks objects toward each other, no matter how far apart they are. But then a young patent clerk named Albert Einstein came along and found a huge problem. See, his theory of special relativity set a universal speed limit. Nothing, and I mean nothing, can travel faster than light. So how could gravity's pull happen instantly? It just didn't add up. Einstein's solution to this puzzle, which he called general relativity, was, well, it was absolutely breathtaking. He said, what if gravity isn't a force at all? What if big things like the sun don't pull on the Earth? Instead, what if they literally warp and bend the fabric of space and time around them? And the Earth? It's just moving in what it thinks is a straight line through this newly curved landscape.
Okay, so to really get your head around this, picture space-time like a giant, stretchy rubber sheet. Now, if you drop a heavy bowling ball, that's our sun, right in the middle, what happens? It creates a big dip, a curve. Now roll a little marble, that's the Earth, nearby. It's not being pulled by the bowling ball, is it? Nope, it's just following the curve in the sheet. And that, in a nutshell, is Einstein's gravity.
And if you're thinking, okay, that's a cool idea, but it's just some cosmic philosophy, think again. You're using it right now. Your phone's GPS depends on this concept every single second. See, the clocks on those GPS satellites are in a spot with weaker gravity, so they tick just a fraction of a second faster than our clocks down here on Earth. If we didn't constantly correct for that tiny relativistic difference, your GPS would be off by miles within a single day. Okay, so we have this brand new theory of gravity as geometry. Now, let's go see where it really flexes its muscles, out in the most extreme places in the universe, where Newton's old ideas just completely fall apart.
This chart right here is going to be our travel guide. It maps out things in the universe by how massive they are and how big they are. Now, down here in our everyday world, Newton's laws work just fine. But we're not staying here. Our tour is headed way up to the top right, where you find incredible amounts of mass crammed into impossibly tiny spaces. This is where space-time gets bent to its breaking point.
Before we jump in, let's do a quick refresher on gravity's basic personality. First, it's universal. It affects everything with mass or energy. Second, it's always attractive. It only ever pulls. And third, it's kind of pathetic. It is unbelievably weak. I mean, a tiny magnet on your fridge can beat the gravitational pull of the entire Earth to hold up a postcard. But look closely at that last word on the slide, usually, because that's about to change.
Yeah, gravity's weakness has an Achilles heel: density. When you take a truly insane amount of mass and you cram it into a tiny, tiny volume, the weakest force in nature wakes up and becomes the most powerful, unstoppable force in the entire cosmos. Nothing can fight it.
Our first stop on this tour, a neutron star. There's one hiding right in the heart of this incredible image of the Crab Nebula. This is the leftover core of a giant star that exploded. We're talking about an object the size of a city that has more mass than our sun. The gravity here is so crushing that it smashes atoms to bits. A single teaspoon of this stuff would weigh billions of tons. Just try to imagine that.
And if you just keep on crushing, if you keep adding mass and density, you eventually get to our final destination, a black hole. Now, this isn't really an object anymore. It's a place, a region of space-time where gravity has won the war against every other force in the universe. It is the ultimate endpoint of Einstein's theory, a spot where space-time has curved so much that it has literally closed in on itself.
And that brings us to the most famous part of a black hole, the event horizon. This isn't some physical surface you could touch. It's a boundary, a one-way door in space-time. The moment you cross it, the curvature of space is so extreme that every single possible path you could take, forward, back, up, down, all of them lead to the center. There is literally no way out.
Now, these extreme objects are absolutely incredible, but gravity's influence doesn't stop with them, not even close. Let's zoom way out and see how these ripples in space-time actually sculpt the entire universe on the biggest scales imaginable.
Okay, check this out.
One of the wildest predictions of general relativity is that when really massive things move around violently, they should create waves in the fabric of space-time itself. These aren't waves moving through space, like sound waves move through air. They are waves of space. The actual stretching and squeezing of the universe sent echoing out from the most violent events imaginable.
For 100 years, this was just an idea on a blackboard. But now we have these incredible instruments that can actually detect these tiny, tiny vibrations. So when two black holes, maybe billions of light years away, spiral into each other and merge, we can now hear the gravitational wave signature from that collision. It's like we've grown a whole new sense for observing the universe.
So you see, gravity doesn't just make stars fall or planets orbit. It's the grand architect of everything. It's what sculpted the massive cosmic web of galaxies and galaxy clusters that fill our universe. It dictates the entire story of the cosmos, its past, its present, and its ultimate future.
This timeline really puts gravity at the center of the story. General relativity tells us the universe probably started in a singularity, a point of infinite density, what we call the Big Bang. It governs the expansion we see all around us today, which is basically a cosmic tug-of-war between that initial outward push and gravity's constant inward pull. And the whole fate of our universe, it all comes down to who wins that fight.
So, we've explored the universe on its absolute largest scales. We've seen gravity as the master of the cosmos. But now, for our final act, we have to journey to the other extreme, to the ultimate frontier, where even Einstein's brilliant theory finally breaks down.
Hey, we're back at our cosmic map. We've been spending all our time up in the top right, in the land of giants, supermassive black holes, and neutron stars. But what happens if we travel all the way to the other corner, down to the bottom left, into the quantum realm, the world of the unbelievably small? And this, right here, is the biggest unsolved problem in all of physics. Einstein's theory describes space-time as this smooth, continuous, beautiful geometric sheet. But quantum mechanics, our hugely successful theory of the very small, tells us that deep down, reality is chunky, chaotic, and based on probabilities. The two theories are both right in their own domains, but they just don't speak the same language.
This leads us to the search for what you might call the holy grail of modern physics, a theory of quantum gravity. This would be the ultimate rulebook, a single framework that can describe both the smooth, elegant curve of a black hole's event horizon and the fizzy, chaotic dance of a subatomic particle. It's the quest to unite our two greatest theories of reality.
This beautiful map you're seeing is the oldest light in the universe. It's like a baby picture of the cosmos just after it was born. General relativity explains its patterns perfectly, but it's also a wall. We can't see past it with our current theories. To understand what happened in the very first instance of the Big Bang, when the whole universe was smaller than an atom, we need that missing theory of quantum gravity. Einstein's vision of gravity completely changed how we see space, time, and our place in the universe. It gave us this epic, sweeping story, from the Big Bang all the way to black holes. But it's not the final chapter. The hunt for its successor is the next great adventure in science. And you just have to wonder, what even more incredible secrets about reality is that next story waiting to tell us?